every volcano on Earth erupts at the same moment. 1,500 of them, plus every hidden vent on the ocean floor. Lava, ash, and fire on every continent at once. And the strangest part isn't the destruction. It's what happens 3 weeks later. When the fires have burned out, the lava has cooled, and the temperature starts to fall, and keeps falling. The volcanoes wouldn't burn the world, they'd freeze it. And Earth has done this before, without our permission. Let's set the terms precisely. Every active volcano on Earth erupts simultaneously, roughly 1,500 on land, plus the far larger number along the mid-ocean ridges. Each one produces a major eruption, not a gentle lava flow. Then everything else about physics, chemistry, and the atmosphere behaves exactly as it does now. Here's what most people picture: a world on fire. Lava spreading across continents, oceans boiling, a scorched planet. That picture is wrong in almost every particular, and the real answer is more interesting. Start with what lava actually does. Lava is terrifying and slow. Most flows advance at walking pace or less, and they don't travel far, typically a few kilometers, occasionally tens. Lava destroys what it touches, but what it touches is a small fraction of any landscape. Even in a global simultaneous eruption, the direct lava damage would be catastrophically local. Communities near volcanoes would be devastated, but most of Earth's surface would never see lava at all. The lava isn't the story. It never is. The immediate killer is much faster. The dangerous part of an explosive eruption is the pyroclastic flow, an avalanche of superheated gas, ash, and rock that races downhill at speeds that can exceed 100 kilometers per hour, at temperatures of several hundred degrees Celsius. Nothing outruns it. It's the mechanism behind the most destructive eruptions in recorded history, and it operates in minutes. Then come the secondary effects. Volcanic mudflows, lahars, form when ash mixes with water or melting ice, and they travel far beyond the volcano itself. Coastal and island eruptions displace enormous volumes of water, generating tsunamis. Within hours, the areas around volcanic zones are gone. That's roughly the Pacific Rim, Indonesia, Japan, the Andes, Central America, Iceland, the Mediterranean, East Africa. But that's still local. Now comes the part that reaches everyone: the ash. Volcanic ash isn't soft. It's pulverized rock and volcanic glass, sharp, abrasive, and heavy when wet. Ashfall collapses roofs. It contaminates water supplies. It's dangerous to breathe. It buries crops. And critically, it grounds aviation globally, because ash melts inside jet engines and coats their internals, causing them to fail. A single moderate eruption has shut down air travel across a continent. Every volcano erupting simultaneously would end global aviation for months. And with it, the fastest routes for aid, medicine, and emergency supplies, precisely when they're needed most. And then the sky changes. Here we reach the mechanism that actually decides this scenario, and it isn't ash. Ash falls out of the atmosphere within days to weeks. It's sulfur dioxide. Large eruptions inject sulfur dioxide into the stratosphere, above the weather. There it converts into sulfate aerosols, tiny reflective droplets. And because nothing rains them out at that altitude, they spread into a global veil that reflects sunlight back into space. The result is cooling. Real, measurable, global cooling. And we know exactly how well this works, because we've watched it happen. A single major eruption in 1991 injected enough sulfur dioxide into the stratosphere to lower average global temperatures by roughly half a degree Celsius for about 2 years. One volcano, half a degree, 2 years. Now scale that to every volcano on Earth at once, with the enormous caveat that this is far beyond anything observed, and any specific number would be invention. What we can say confidently is the direction and the rough magnitude class. A drop of several degrees, sustained for years. And several degrees is enough to break civilization. Not through cold itself, through agriculture. Crops don't fail because it's uncomfortable. They fail because growing seasons shorten and frosts arrive out of schedule. Reduced sunlight slows photosynthesis, and global food production is not spread evenly. It's concentrated in specific regions during specific months, and those regions failing simultaneously is a problem no reserve system is built to absorb. There's precedent for this too, at a far smaller scale. A major eruption in 1815 was followed by what became known in the Northern Hemisphere as the year without a summer. Snow in June, failed harvests, and widespread food shortages across Europe and North America. That was one volcano. And the following year was merely cold. Now the twist most people don't expect. Volcanoes emit carbon dioxide, which is a greenhouse gas. So shouldn't the eruption warm the planet? Eventually, but the timing works against itself in a strange way. Sulfate aerosols fall out of the stratosphere within a few years. Carbon dioxide persists for centuries. So the sequence would be years of severe cooling, then the veil clears, and Earth emerges into an atmosphere with elevated CO2 that stays elevated long after. Cold first, then warmer than before, for a very long time. Two opposite climate disasters from the same event arriving in sequence, and the recovery from the first delivers you into the second. And here's the part that reframes everything. Earth has done this before. Not simultaneously, but sustained. Several times in Earth's history, colossal volcanic provinces erupted continuously for hundreds of thousands of years, flooding entire regions with lava and pumping gases into the atmosphere for a period longer than our species has existed. The largest of these coincide with the most severe mass extinctions in the geological record. Including the end Permian event, the closest life has come to being erased entirely. The leading explanation isn't lava, or ash, or heat. It's the atmosphere and the oceans, gas-driven climate disruption, ocean acidification, and oxygen loss in the seas, sustained for far longer than any ecosystem could adapt to. So volcanoes have genuinely ended worlds, just never quickly and never through fire, which leads somewhere unexpectedly clarifying. We instinctively fear the visible catastrophe, the lava, the explosion, the thing that looks dangerous. But almost every planetary scale disaster works the same way, and it isn't the one you can see, it's chemistry. Something invisible enters the atmosphere or the ocean in quantities that seem small against a planet and changes a system that everything else depends on. The volcano is only the delivery mechanism. The most dangerous thing about a volcano isn't what comes out of it burning. It's what comes out of it as gas. So here's tonight's question. If the real threat is always the invisible part, what do you think we're currently underestimating? Because it doesn't look dramatic enough to be frightening. And how would we even know? Every question creates a new reality. And reality is just one version of the truth. Every possibility deserves exploration. The next one begins with a single question. What if? Subscribe and explore what comes next.